So let's say we have a regression function of income that are determined by dummy variables or indicator variables. And these variables take on a value of either 0 or 1. So the output of income is determined by the beta 2 of male. If 1, this beta 2 will have an effect of income. And then if it's female, the variable will equal 0. Similar to the 1 and 0, the college variable of beta 3, it will, if the individual went to college, it will have an effect of beta 3. If the individual did not graduate from college, this will have no effect. For the last variable, let's recall the concept I went over of the interaction variable. So male times college, this coefficient given by gamma will represent the interaction variable between if the individual is male or not, and if the individual is went to college or not. And so we can see that these two here are based off the intercept. So the male and college, because they're not interactive variables, interactable variables, that will only affect the intercept of the income, and the gamma slope of the interaction variable will only affect the slope. And so the expectation of income we can write as beta 1 plus beta 3 college if the individual is female, and we include the beta 2 term if the individual is male, because beta 2 is given if the individual is male or not. And then the last variable of gamma, because for college, we don't know if the male went to college or not, so we'll leave that as the variable itself. So like I said, if for the variables of just the binary variables, these only affect the intercept. So if college is held constant, if we're visually inspecting the differences between if the individual is a male or not, or a female, then this would be the difference right here of beta 2. All right. However, let's say we want to represent the binary function of a female variable instead of male. And so we could just subtract 1 from the male variable to obtain the female variable. But now our other coefficients that we used here are based off the male variable. And so we have to kind of alter all these college and beta 1 variables. So our new beta 1 for our female is given by beta 1, the intercept, and beta 2, which is male, because we're subtracting 1 from beta 1 and the male coefficient. The new beta 2 for female will be given by negative beta 2, the negative male. And then our beta 3 for college stays the same, because if the female went to college, then we still have our beta 3 coefficient. All right, so let's get back to our original equation right here. If we're differentiating the output in respect to male, notice how it's different from here, because this we're measuring just the output raw value, output value, but in this part we're measuring the derivative or the change. And so if we're deriving that in respect to the male variable, we'll just get beta 2 right here if the male did not attend college, and if he did attend college, then it will be given all these coefficients here. So generally, it will as you can see here, because the interaction variables actually affect the slope and not just the intercept, we can see that there's a sufficient increase because the male went to college. And so we can interpret it. This is pretty straightforward, but we can interpret that in this equation here. So beta 1 accounts for all individuals, whether it's female or male, or whether they went to college or not. And if the male didn't go to college, then they still get the beta 1 coefficient. They still get the beta 2 coefficient for male, but they don't get any of the college variables. So this is 0, this is 0. If the male went to college, then we include the college and the male times college. Now you're probably wondering why this actually counts as a slope, because if male is 1 and college is 1, then intuitively this can just kind of be seen as like similar to beta 2 and 3. That is a very good thing to ask, but again, recall what I said about the interaction variables. So this is kind of further measuring the effect of if the male went to college, because obviously these two already account for if the male went to college, but this is like further inspecting if there's any more effect, unobservable effect of, if the male went to college, do they get any more advantages than just these two parts of the equation? And then if the female did not went to college, then they would get the beta 1 right here, and then beta 3 because she went to college. All right. Using inferencing or hypothesis testing on indicator variables, pretty similar as always. Null would say all of them would equal 0, including the gamma. And then the alternative would say at least one of them is significant or not equals 0. So we'll use the same F statistic. If it's greater than the critical value, we reject. But another test we could use is what we call the Chow test, done almost always done in software. And then, so what the Chow test does is similar to the reset test. It'll kind of look through all the combinations of interaction terms. So in this function right here, we didn't include like female college, or we didn't include like grad school if that's part of our data hypothetically. So we'll kind of go through like all of those combinations and then look for kind of search the ideal model. But yeah, indicator variables, they have some different factors than discrete variables or continuous variables, but more or less they kind of work the same way. Heteroscedasticity, if we factor into that, it is different. The way we correct for it is different, but intuitively they should be the same. The unique part of it is that they take on a value of 0 or 1. All right, but speaking of heteroscedasticity, that's what I will go over in the final video of my linear regression part of the series.